back. The mean value theorem for integrals. If f is a continuous function on closed interval ab, then there exists a number c in open interval ab such that the value of f at c is the actual average of f. What was the average of f? It is 1 over length of the interval times the integral from a to b fx dx. Okay. By cross multiplying by b minus a, what do you get? F at c times length of the interval b minus a is integral a to b fx dx. See, geometrically what this means is there is a number c in your interval ab such that the entire area under the curve fx from a to b is that value f at c times length of the interval. So there is a rectangle whose area is equal to the area under the curve. All right, that's a geometric interpretation. How do we prove this? Well, consider the function capital Fx, which is integral a to x ft dt. You have seen this in the discussion of the fundamental theorem of calculus. So this is partial areas under the curve f. Starting from a, you move x, the upper limit, you get different areas, right? Varying areas. That's your area function capital F. What do we know by the fundamental theorem of calculus part 1? This capital F is continuous, all right, on the closed interval AB. Moreover, this capital F is differentiable on open AB. Moreover, the derivative of capital F is little f. All right. So, what else do we know? Well, capital F is continuous, right? So, use the mean value theorem for continuous function. What does it say? For any continuous function on a closed interval AB, there is a number c in open interval AB such that the derivative is slope of the secant line joining the endpoints. All right, let's go again. Mean value theorem for any continuous function, actually I should say continuous on the closed interval and differentiable on the open interval. You need differentiable on the open interval. There is a number c such that derivative at c is equal to the slope of the secant line joining the endpoints. Okay, but what do we know f prime c to be? Well, f prime, capital F prime is little f. Okay, now let's figure out what is capital F at b. Capital F at b is integral a to b ft dt. Okay, x becomes b. Well, this is, right? This is the overall integral. What is capital FA? It is integral a to a. It's only the upper limit that gets changed. What is integral a to a of any function? There is no width. There is no area if there is no width. So that is 0. So in my expression here, capital F is 0 and capital FB is my integral a to b fx dx. Notice I've written fx dx and ft dt here. Well, it doesn't matter, you see. There is no more x here, so I have simply replaced the t by x. So where did this 1 over b minus a come from? That's that. So we use the mean value theorem for continuous and differentiable functions. I should say differentiable function, to get me the mean value theorem for integral functions. So what have we said? There is a number c such that fc is 1 over length of the interval a to b integral a to b fx dx. Okay, let's use this. identify number C in, so a number, right? You are guaranteed one number. There could be more. So they're asking you to identify at least one number C in the interval 0 to 3 that satisfies mean value theorem for integrals, right? The function fx equals 3 plus x cubed. So remember, that was our example 1, 3 plus x cubed on the interval 0 to 3. So you want to find some number C where the average value is equal to the value of f. So f at C must be the average value. Well, f at C, because of the function rule, that is 3 plus c cubed, right? Instead of x, I have c. This integral average value we have already calculated in example 1, that is 39 by 4. I simply move the 3 over. Overall, I get c cubed equals 27 by 4. C is therefore cube root. Okay, this is a real number. The other two cube roots are complex numbers. So you found one which is in your interval 0 to 3. Okay, so this completes. Oh, by the way, before I even apply this, remember this is a polynomial, therefore it is continuous. You needed continuous function to apply the mean value theorem. All right. Okay, so this completes the theory for section 5.4. We'll continue with problems in our next videos. Until then, bye.